Good afternoon, everyone. My name is Douglas Botterdew. I'm with KukerRanken, and it is Wednesday at noon Pacific Standard Time. So that means it's time for another Lunch and Learn. And today we're going to be talking about choosing a LiDAR sensor. We've got quite a bit of data to go through, and looking forward to sharing what we have. So without any further comment, I'm going to go ahead and get right into it here. All right, so we're going to talk about choosing a LiDAR sensor here. Now, a couple things that I want to point out that LiDAR are used for that might not be common knowledge. This isn't really a lot to do with what we happen to use LiDAR for, but this is an example of a castle that has been scanned using LiDAR and colorization point cloud techniques. And this is being used for import into a video game. So in other words, this is one of the ways that we can capture, instead of having to draw and animate or create some of these assets for different video games, we can scan existing things and then modify them as we'd like to view. So for example, if you've seen Grand Theft Auto version 3, and I believe the newest one as well, has got a lot of buildings in Los Angeles that were all scanned using a Pegasus scanner. So other places where we use them, though, or LiDAR systems, is for earthworks and survey, et cetera. LiDAR is a massive, massive time saver when it comes to things like earthworks, if we're doing volumetrics or contours, topos, and typical kinds of things that surveyors use. If we need digital surface models, this is a really great tool that allows us to access the contours and be able to output this data very, very rapidly. So for example, a bowl piece or a mountain piece like this will take longer to fly than it will take to actually extract those contours or the topographical map that we're looking for. In fact, one of the devices we're going to be looking at is called the 1-foot contour monster. So let's just dive into some of the differences in photogrammetry and LiDAR so we understand a little bit more about it. We're probably all familiar with photogrammetry, where we have RGB or red, green, blue cameras that are shooting photographs. Generally, we'll be shooting these straight down or shooting a combination of straight down called nadir shots and oblique shots, which come more from the side. And this is a great way to work. One of the things that we've been doing in photogrammetry for years is mapping from aircraft. And of course, now we're doing this with LiDAR as well. The photogrammetry is a little different. First of all, photogrammetry can only occur during daylight hours. The camera needs to be able to see what's on the ground, so we have to have decent lighting. For photogrammetry, because we're dealing with usually hundreds and more frequently thousands of photos that we're going to be stripping together or stitching together in a post-process tool, we need a fast computer system that is capable of managing these massive files. So if you could imagine shooting, say, 42 megapixel pictures over a 250 acre plot, you're all of a sudden going to be dealing with roughly 3,000 42 megapixel images. That's an awful lot of storage. And it's also being processed in real time. And this is why we have to have high-speed computers, is because we're processing every single pixel. Additionally, with photogrammetry, we require very high overlap as we're flying over our subject. And so typically anywhere between 75 and 90% overlap is required. So in other words, with photogrammetry, we have heavy areas that are overlapping with each other. With LiDAR, that overlap can be quite slight. So it's not uncommon at all for us to be seeing a 20%, 25%, 30% even overlap with LiDAR. And we're going to look at some of that here in just a couple of minutes. Now, one of the things as well is the GSD, in other words, our ground sampling distance, is variable depending on how high at which we fly. So if we're flying at say 65, 70 feet, we're going to be getting about a half a centimeter per pixel. If we fly at 120 feet with a typical Autel Evo 2 or 1-inch camera, we're going to be seeing that captured about 1 centimeter per pixel. So the altitude is pretty important when we're looking at some of our GSD and looking at what kind of detail we want to get. And we can use photogrammetry to generate a point cloud. And in fact, down below this image is something that I shot yesterday afternoon. We shot that using an Autel Evo 2 version 3. We were testing out some of the new mission planning capabilities in the V2, or excuse me, the V3. And this is a point cloud that you're looking at down here. So while this was generated from photogrammetry, that is a high quality point cloud. When we talk about LiDAR, LiDAR is a little different. One of the main benefits of LiDAR, aside from the fact that, of course, it's remarkably fast, is that LiDAR can operate at night if we don't need to colorize our point cloud. The reason that we can't colorize a point cloud flying at night is because we do use RGB camera to colorize our point cloud in the LiDAR world. So if we don't care about colorization of a point cloud, then we can fly at night, which is great because that means there are fewer pedestrians on the street. It means there are fewer people and cars that are around, fewer things that we have to worry about. Plus, it may well be that your organization has got quite a backlog of work. And one of the things that you can do to cut that backlog down is continuing to capture data, whether it's daytime or nighttime. Now, one of the other things about LiDAR is LiDAR is basically just generating a large Excel file. There's no pixels. It's all just binary ones and zero information with no pixelization attached to it at all. And so it doesn't take a very fast computer to process at all when you're dealing with LiDAR. Now, you do want to have a reasonably fast machine if you're going to be colorizing, but again, we don't need that super fast, brilliant computer. Then we don't require that high overlap. We already spoke about that just a moment ago. And ideally, we're typically going to fly somewhere between 40 and 80 meters or between 130 and 260 feet with our LiDAR system. That'll be variable depending on where you're at. For example, the image that you see directly below, there are several 100+ foot tall trees in that particular environment that we're looking at there. And so we want to be sure that we are capable of getting high enough to get over trees, but low enough that we're still getting good beam return off of our LiDAR system. We'll look at what that looks like in just a moment. When we're done with the LiDAR, we end up with a precision point cloud. So it's a little different than what we end up with when we're doing photogrammetry. Now, there are lots and lots of different LiDAR devices to choose from. Without going into all of them, you can just see some of the different brands that are there. But how does a LiDAR system work? Well, what happens is we have that sensor that's up in the air, and it's got a device inside of it that's spinning, and that shoots a laser beam down. And that laser beam then strikes something, and that pulse comes back and goes back up to there. And we use a combination of the speed of the drone coupled with the time of the return, or how long it takes to get back up. And this is what generates the data sets that feed us our distances, or our ranging and distance. And then we calculate all that against the altitude and the XYZ of where the drone is. And that's what gives us a very precise echo position, or a very precise position of what's down there on the ground. They all work essentially the same with a few exceptions. But all of these are mechanical LiDAR systems, so they have spinning parts that send that laser beam out and into the wild and read that beam as it comes back, returning to it. Before we get too deeply into other forms of LiDAR, I want to put off to the side this concept of what is called solid-state LiDAR. Solid-state LiDAR is very much coming to our industry. It currently is heavily used by the automotive industry because of its lightweight, its low power consumption, and the quality of output at short ranges. And by short ranges, that generally has been somewhere in the range of 30 to 40 meters. However, we are seeing LiDAR systems that can come out and do quite a bit more. So this one that you're seeing off to the side here, this is a MapTech drone system made in Korea. And on it does have the Levox solid-state LiDAR system, low power consumption. It doesn't weigh anything. This is being picked up on a very small platform drone. The cost is really effective when we get into solid-state LiDAR, and the size is about equal currently to the size of a typical mechanical LiDAR system. And we do have some challenges with solid-state LiDAR, although those challenges are diminishing about as quickly as I'm speaking to you now. So, for example, 2 years ago, when we started putting solid-state, or we saw solid-state LiDAR systems being put onto automobiles, those systems could only run a very, very short range. And so they were typically about 30 meters at most. For drone work, that's just not far enough. 100 feet isn't going to get us where we need to go. However, in the course of just basically 6 or 8 months, we started seeing longer range solid-state LiDAR. And even today, we're seeing even greater LiDAR. So this one you're seeing here off to the side has a range on it of approximately 120 meters. So we're able to get, good 300-foot beam with pretty solid returns. However, we're still very much maturing the solid-state LiDAR business, but bear in mind that solid-state LiDAR is coming. One of the things about solid-state LiDAR as well is that we have to fly just a little bit slower, and we can't capture a 360-degree view like we can with typical LiDAR. But for drone flight, we don't capture 360 anyway. So it does look like solid-state LiDAR is going to be a great addition for our drone systems. Let's talk about some things we need to consider. When we're choosing a LiDAR sensor, we want to know that we've got a LiDAR sensor that's got enough returns. So some systems go as high as 5 returns. 3 to 5 or 3 to 4 is really more common. Some are two beam returns. So what'll end up happening is we're sending that information down, but how many times is that coming back up in and being counted? That all helps with the speed of what we're trying to do. One of the questions as well that we want to ask is, how far can that LiDAR beam travel and capture good data? You're going to see what it looks like when it can't travel far enough in just a moment. But what we want to be able to do is make sure that we are getting good, solid, confident returns that are coming back so that we've got data that we can trust, especially if you're an engineering firm and you're working with digital surface models and you need to get through foliage and brush and overhangs and those kinds of things. It's important that we've got confidence in our data. Now, some systems also combine the LiDAR beam with a photogrammetry camera. So if we step back here to the solid state system, you can see there's a photogrammetry camera, an RGB camera here, and then there's the LiDAR system that's here. As well as when we start looking at things like this TrueView 515 that you see right here, that's got an RGB camera on it. So does this 410 over here. The DJI L1 has got an RGB camera on it. So there are lots and lots of different ways that these can be put together and work. But if we're going to do any type of colorization, if we're going to add reality capture type color to our point cloud, then we need to have an RGB camera. There are several different systems out there. For example, GeoQ manufactures LiDAR systems that got anywhere between 1 and 3 cameras. So on their higher end systems, they have stereo cameras so that we're capturing obliques at the same time as we're capturing the nadir and the LiDAR information simultaneously, which makes for a very, very fast workflow in post. Then the last is the quality of alignment, and this is a big one. What you're seeing off to the right-hand side here is a scan with a lower-end LiDAR system, and you can see that there's quite a hodgepodge of strips. I don't want to go into all the technology and how all of this works, but understand that in photogrammetry, every time that aircraft goes back and forth, it's just simply shooting pictures along those lines, and then we use the XYZ data combined with pixel data, combined with match data, key match data to lock those pictures together or align those pictures. LiDAR doesn't work that way. Every path is an individual strip, and then those strips are assembled, and then the strips are stitched together. What you're seeing here is a number of different strips, and if you count those, you can see 3 very major strips right here that are set apart, and you can see those all the way through, and then you can see other strips going in the other direction, and again, they're not lining up. This is a big problem. This means that our data is not confident. This means that our data cannot be measured accurately or proficiently. So let's look at how that comes out in a real world and as we go through here. I also mentioned foliage and density is a really important consideration. This depends on where you live. If you live in desert environments, such as we're based in Las Vegas, Nevada, it's really hard to find an area that is heavily covered with foliage. On the other hand, you go up to where a great number of our customers are up in the Pacific Northwest, there really aren't very many flatland areas that aren't covered in green. So the needs between those two different regions, those two different ecosystems are quite different. However, even in, say, a desert area like down here in Las Vegas, or today we're coming to you from St. George, Utah, in these areas, there's just not a whole lot of trees, but we're still going to use a higher end LiDAR system. One, because it makes no sense to buy a cheap system, a less confident system when you're in desert environments, and then a more confident system when you're in those Pacific Northwest environments. Just use the same LiDAR for both. So buy the best you can buy, access the best you can access, whether you're going to rent it or buy it. Get something that goes beyond what your specific needs are. Now, to point some of this out to you, here you're seeing a very gentle slope. This is in a desert environment. Even under most of the brush and the trees, we've got a good solid foundation. You can see here, whoops, right here. It's kind of difficult to see. You'll see this better in future slides, but there's a gap. That means that the LiDAR could not penetrate that tree cover and get through it. Same thing is happening up here where we have a huge gap. And that again is LiDAR data unable to penetrate trees. Then we come down here, and this is in the central part of the U.S. in very heavy oak and birch and sumac, lots of large broadleaf tree, and yet you can see we have an incredibly solid surface. So we're seeing all the way down to the ground through all the trees. So that is the difference between, say, a $30,000 LiDAR sensor and a $300,000 LiDAR sensor. So yes, the quality does cost. Right, here we're looking at a very popular LiDAR sensor. This is the DJI L1 system. And we can see that we've got some real problems in the stripping. So the strips are not properly aligning. This is being put together in DJI Terra. So it's using the DJI software to process the LiDAR data. So we can see strip problems in the overhead. We see strip problems when we look at it in a more planar view. But what's really important is look here. We've got fairly clean area. There's not a lot of foliage other than some grass, except for some basic trees. Underneath these trees, we have no data at all. And here we've got a fall off. So from an engineer, civil engineer's perspective, or if you're surveying, et cetera, if we have a drop off here, we have no idea what we're looking at. You can see here, there's a vehicle right next to the trees. So is this a walking ramp? Is this a creek? Is this a set of stairs? What's underneath that tree that we didn't capture? That's kind of a big deal that we need to be able to look at. So here's how that stripping works. This is operating in DJI Terra here. And as we zoom in on those strips, so you can see where the strips are not aligned, let's zoom in very, very deeply. And when we zoom in deeply where those strips are, now let's flatten this out. And you'll notice that not only are the strips not properly aligned, but you'll see one strip is separated in strata from the other. So look at that. You can see down below here, there's one strip down below and another strip up above. In other words, they're not aligning the way that they need to align. This is not useful for us and actually can be quite detrimental if you're not familiar with these software tools and not understanding quite what you're looking at. So that's one problem, that strip alignment that I mentioned. And this is something that I believe DJI is working to resolve in their L2 system. But needless to say, it's something to be aware of. Now, here's another shot with one of the L1 systems. You can see there's a lot of black holes under the tree. Under these trees, those black holes indicate that there is no data there. We cannot see beneath the trees. So we don't know whether the ground is a depression or whether the ground is flat. Is there a hole there? We have no way of understanding anything that's there. Now, off to the side there, you can see that we've got a little bit of a reservoir that's completely dried out, but at least we're pulling data. And then up above, you can see where we're able to capture other kinds of data outside those trees, but the trees are covering everything, and it creates a real issue because we can't pull data from them. So in some areas, for example, up in the Pacific Northwest, the L1 can be a challenge. There are ways of getting around those challenges, but they end up costing us a fair amount of time. If you're spending a fair amount of time ameliorating other problems, you may have found yourself in a better position to have spent just a little bit more because your time is valuable. And let's face it, if you work in the survey industry and you're like most everybody else in this industry, you're behind. You've got a backlog. And one of the greatest benefits of LiDAR-based systems is we can frequently help you clear those backlogs very quickly. Let's continue to look at a few different systems though. Here we're looking at what's called an HR system. And again, we don't see any of the strip problems. We see everything aligned. The reason we see the changes in color here is because they're changes in elevation. And this is a water drainage area that's also been turned into a city park. Notice with all of these different palm trees that are up here, most of the way through, we've got really good solid data. We can see all the way through to the surface, which means we can pull a solid surface model. So this system here comes in with the drone right around $60,000. It's a really great median system. And if you're running back and forth between heavily vegetated areas and desert areas, that is a really great median starting point. Now, maybe you live in, again, a heavy vegetated area, so you're going to need something that's got a little bit more data to it. We're going to look at that in just a moment. But what you're seeing here as well is this is also the UHR, and this is an incredibly heavily wooded area up near Seattle. You can see there's a bridge right here going deep down into a gully, a wash. And here I've just generated a quick profile of that area. And again, we can see some pretty solid data right there. So with that in mind, I'm going to open up a different window here and show you a little bit about how that looks or how that overall works. So I'm calling up what's called this is MD Infinity. What you're seeing is a live view of data that's online. So we can see a piece here where there's a home up on top of a hill. They're doing some earthworks down here to build another building down here where they've leveled that out. Let's generate a profile and see how well this UHR, this $60,000 drone did. So we're just going to real quickly drag and draw across here. I'm going to draw across that house and down on the side of the mountain. And you're seeing that build the profile in real time there. Notice that as that builds up, and again, this is live, this is coming in over the internet. And if you'd like to access this model, I'm very happy to share the data model location with you. Just drop me an email and I'll send this over. But we can see we've got really great profile data that's coming in down here. Oh, I moved my mouse, so now it's rebuilding. The only place where we have gaps is actually underneath the roof line, the eave line of the house. So this is what a $60,000 system can bring to the table. It doesn't have to be a really high-end overall system. But we'll look at a couple of others real quickly here. Got my share on that one. And let's go back to our death by PowerPoint. So this right here is what is called by GeoQ or Microdrone the Vegemite. Now it's just kind of a nickname that we lovingly refer to. This is one of their newer systems. This guy comes in, he just flies on the same aircraft platform that you saw from the other one. It's just a higher grade sensor. But notice here we have heavy vegetation all the way down right here to this edge, and then again heavy vegetation. In fact, you can see the area right here in the map up above. It's lots of trees over top of a riverbank or over top of a river run. Well, what you're seeing right here, this depression that's down there very, very low, that area that you're seeing right here is actually showing underwater. Now, all that does is lets us know that the sensor is able to see underwater. We can't measure that. It's impossible to do accurate measurement in this particular environment because as the laser strikes the water surface, the laser then bends, and so we can't trust the measurement. But what we can see is we can see where the very edge of the riverbank is right here, and same thing on the other side, and we can even see overgrowth where we've got plants that are growing into the water right there. So that's really the benefit there is this system is very clean. And notice that the strip alignment that we're seeing up here is very, very clean. That's the flight path of the aircraft. And again, we see that down here as well. So we've got a height map that's generated here. So this heat map indicates the height of the various foliage that's around. The area that we see in blue is where the river is. If we had not been running the secondary camera there, that blue would just show up as a solid black. So let's step on to another system here. There again, we're zoomed in just a little bit. We can see that overhang into the water. We can see what's going on there. Now let's really step it up. We're going to look at a Regal system. This is one of the top-end drone-based systems. And in fact, until just a year and a half ago, this puck was only flown on manned aircraft, be it a Robinson helicopter or maybe some kind of a small fixed-wing system. This is about as good as it gets without getting into the $1 million plus range. So you can see that we have solid surface all the way across the bottom here. We're seeing through all the trees very cleanly. Now we've got an interesting thing down here. We've got a little hump. See that hump? Any idea what that might be? So what that's going to be, let's just zoom in a little deeper so you can see that tiny hump. Let me go to my next slide here and zoom in. Does that give you a little bit more of an idea? That is a train track. So we're getting amazing detail out of this higher end system to the point where we have measurable train tracks. I'm starting to get a little behind here, so I'm just going to get through right to my summary. One of the things to be aware of is, LiDAR makes everything available to everybody. It's a fantastic system when we need speed and we need very, very accurate outputs, and we don't have the time to wait for photogrammetry to operate. So I've run a couple of numbers over here. So if we fly a 50-acre site, we fly it with photogrammetry. Let's say that we've got a reasonably fast computer. It's got 32 gigs of RAM. It's got solid-state hard drives, has a graphics processing card. It takes about 20 hours to process that at full resolution. So it is not a fast exercise. On the other hand, LiDAR can cover that very same area and process and spit out data in about 30 minutes on that same computer. So again, that computer time, that computer horsepower time, it saves you a tremendous amount of money on the back end or back in the office. Your field time is going to be somewhat similar. Remember, with photogrammetry, we have to have very tight overlap. When we're dealing with LiDAR, we don't need tight overlap. So we can save some time on the flight, but the processing time is where all the difference can happen. And in fact, we have a couple clients up in the Northwest that are flying LiDAR, and then they're doing field side processing. So when the aircraft comes down, they pull the data card from the aircraft, they put it into a laptop in their truck. They're running fairly fast. They wear laptops, and at KukerRanken, our sales professionals can help you choose which kind of laptop you're going to want if you want to do field side work. But they're spitting this data out right there field side. That's incredible. We go from planning the flight, executing the flight, to delivering the flight all in one place. It's very, very fast. And again, this is one of the greatest tools to help clear backlogs or to capture very precise data. And when you have repeatable flights, it becomes even easier. You start registering different flights with each other to draw differences or onion skins. We can either do a difference map and see the difference between what did it look like last week, what did it look like this week, or we can onion skin it to be able to peel away the differences as we're going through progress reports and monitoring. So again, LiDAR is just so much faster and time saving. Additionally, while for some folks that upfront cost might seem to be a burden, the amount of sheer time that it saves actually pays for itself. We've got one client that paid for their LiDAR aircraft in 2 flights or in 2 projects. And that's not an uncommon story from a lot of our customers. Needless to say, we appreciate you being here at our Lunch and Learns. The upcoming Lunch and Learn that we have next week on March 15th is featuring Matt Kowalski, one of our most popular presenters. And Mac's going to be doing an introduction to MS-CAD. So we look forward to seeing you at our next Lunch and Learn next Wednesday at noon. And here's my contact information if you have any further questions there. Again, my name is Douglas Spotted Eagle, and I can be reached at the email address that you see there. This Lunch and Learn will be available on our website as well as on our Facebook page in a day or two. So I want to thank everybody for taking the time to come and spend your afternoon with me. We know that your time is valuable, and we appreciate you sharing some of it with us. So until next time, folks, we'll see you next week. Be safe out there.